was, I would show you. It was on a baseball field. Pretty great. No, college baseball field.
St. Martin's?
No, it wasn't. It was over in Idaho. The college that my dad was the athletic director for, and I worked at. I played baseball there for a little while. Anyways, long story. Equilibrium and stability properties of LTI systems. So lecture 5.2. For a system with LTI state space model given here. So this is our standard state equation, x dot equals ax plus bu. And the output equation, y equals cx plus du. So we learned last semester how to construct these objects. The model is in equilibrium state x naught if all time derivatives of the state vector, so the first time derivative, second, third, etc., are the zero vector. This implies that ax naught plus bu is equal to 0 because x dot equals ax plus bu. For constant input u bar, this implies, so we have ax naught on the left-hand side, and on the right-hand side we have negative bu bar. I'm going to put just u bar there. It is a vector, but putting a vector and then a bar is hard to see. So I'll just put u bar. If A, matrix A, is invertible, as is often the case, there is a unique solution for a single equilibrium state. Interesting. Well, I lost that page of my notes, but that's okay. So we're solving for x naught vector, the equilibrium state. If A is invertible, you can left multiply by A inverse on both sides of the equation, and you get negative A inverse B U bar. Great. So we have our solution for the equilibrium state, right? If x is perturbed from an equilibrium state, x naught, the response can do one of three things. So perturbed means it's like moved a little bit away from that state. So if you move it away from the equilibrium state a little bit, the response can do one of three things. It can asymptotically return to x naught, and we call this type of system asymptotically stable. It can diverge from the equilibrium state, and in that case we say that the system is unstable. Woo. Or the third possibility is that the state can remain perturbed. Yes. You're batting 1,000 so far, Anna. That's good. Okay. So remain perturbed or oscillate about x naught with a constant amplitude. In this case, we say that the system is marginally stable. Great. So this is like high level how we think about stability, okay? Now, a phase portrait is a parametric plot of state variable trajectories with time being implicit. You guys have done parametric plots before, right? Like, oh, you guys did like cardioid plots and stuff. Like what is it? Pre-calc? Is that when you do that stuff? Like if you have x, y coordinates and they're given, so x, y, and the points are given as being like sine x, sine, not x, sine t, cosine t, and where t is your parameter that you vary. So t would be implicit, and this would just go around and around in a circle. You guys remember that? Yeah. Parametric plots. Pretty sweet. Anyways, those are, if you do a parametric plot where your x and y, instead of being x and y, you have them being your state variables. So like x1, your first state variable, x2, your second state variable, and t is time, and you increase time. So as you increase time, you're going to have some response that'll happen, right? So you're always in some state. We're not doing quantum mechanics here. So your system's always in some state, right? Some concrete state. We like that. You could kick it. It's there, right? So for every moment in time, the state vector maps to some value, okay? Gives you some value in what we call the state space. That's why we call it the state space. State space model in the state space. So you can think of the solution to the system. You can think of the response of the system as having this trajectory through state space. It moves around in state space. And that is a really, really useful way to understand systems, especially if they're nonlinear. So linear systems, the phase portraits are not super exciting to look at. They tend to be relatively obvious. And we can solve linear systems directly. It's not hard to solve them analytically. Whereas for nonlinear systems, we can't. So looking at phase portraits for nonlinear systems gives us insight into how they're working, like what their properties are. So understanding the phase portrait in the linear system is useful for what we're about to use it for. But for nonlinear systems, it's really, really great. So that's what we'll do right now is we'll look at these three phase portraits. So take, say you had a second order system. So you have two state variables, x1 and x2. And you have an equilibrium value at the origin of each of these graphs. Let's say that you start at some arbitrary state out here. If your system is asymptotically stable, then no matter where you start, it's going to approach the equilibrium state as time goes to infinity. It'll approach it asymptotically. So that would be an asymptotically stable system. Their phase portraits would look like that. So this would be the free response, right? Just let it go and whoosh. Marginally stable system, if you perturbed it from an equilibrium position, you let it go, then we would have this either it would stay still, it wouldn't move at all, or it will just go round and round this equilibrium value and it won't grow. None of the state variables will grow without bound. It'll just stay there. But it won't go to zero, it won't go to equilibrium, it'll just go round and round. That's marginally stable. If the system is unstable, then at least one of these variables is going to blow up to infinity. So it could be both too. So in this case, like I'm showing these sort of like cool circular paths, but it doesn't have to. It could just go straight out too. But it doesn't look as cool. So I wanted to make it look cool. So that's an unstable system. So that's how we can use a phase portrait to have a feeling for the system. If you start out the trajectory there, it goes off to infinity. That's unstable. Okay. So these definitions of stability can be interpreted in terms of the free response of a system as described below. I'm sorry we are going to go a few minutes late, but I hope you guys don't have too many commitments after this. You shouldn't, because my class is your life, right? Okay, good. Using the concept of free response, no inputs, just initial conditions, which we covered a minute ago, we define the following types of stability for LTI systems. So we're going to take those concepts from above, we're going to reinterpret them in terms of the free response, okay? So, 1, an LTI system is asymptotically stable if the free response approaches an equilibrium state as time approaches infinity. So there's an interpretation in terms of free response. An LTI system is unstable if the free response grows without bound as time approaches infinity. So that would be an interpretation of unstable using the free response. And then finally, an LTI system is marginally stable if the free response neither decays nor grows but remains constant or oscillates as time approaches infinity. These statements imply that the free response alone governs stability. So if we use these statements to be our definition, which we will in this class for the most part, unless I explicitly say otherwise, we're going to use these definitions. Recall that the free response, YFR, of a system with characteristic equation roots lambda I with multiplicity mi for constant ci is that y free of t is equal to the sum over all of the roots of the characteristic equation of a constant ci for each of them times the t raised to the multiplicity mi minus 1. So most of the time the multiplicity is 1, but if you have a double root, it's 2. A triple root, it's 3. Times e to the lambda I t. Great. Each term in this sum will either decay to 0, remain constant, or increase without bound, depending on the sign of the real part of the corresponding root of the characteristic equation. So lambdas are what govern the stability of this. If lambdas are negative, the real parts are negative, then we're always going to get an exponential decay. If the real parts are 0, we're not going to get a decay or an increase. And if the real parts are positive, we're going to get a growth, an exponential growth. Okay? There's a little bit of subtlety that comes in because of this multiplicity t factor, but the exponential always dominates the time or the t factor here. So unless you have the marginally stable case, that's where it gets a little bit tricky. In other words, for an LTI system, the following statements hold. 1, an LTI system is asymptotically stable if for all lambda, so all of the roots of the characteristic equation, the real parts are less than 0. So you have negative real parts for all of your roots of your characteristic equation. 2, an LTI system is unstable if for any lambda, the real part's greater than 0. So if you have any lambda, any root of your characteristic equation that has a positive real root, then you are in trouble. You have an unstable system. And an LTI system is marginally stable if for all of the lambdas, the real part's negative or 0, and at least one of them has to actually be 0. The real part has to be 0 in order to get marginal stability. This is the one that we should use in most cases. It's the one that's boiled down to the sort of meat of what we need. But let's look for just a moment at the stability defined by the forced response. An alternative formulation of stability is called the bounded input, bounded output, or BIBO stability, and states the following. The system is BIBO stable if every bounded input yields a bounded output, and a system is BIBO unstable if any bounded input yields an unbounded output. So this is slightly different. In terms of BIBO stability, marginal stability then means that a system has bounded response to some inputs and unbounded to others. For instance, and this is one of the interesting edge cases, a second order undamped system response to a sinusoidal input is at the natural frequency is unbounded, whereas every other input yields a bounded output. So if you think of our spring suspending a mass, if there was no damping on it, and you force it and you have a forcing function at any frequency, you're going to get a response that's finite at that frequency. Unless you do it right on resonance, right at the natural frequency. In that case, you get an unbounded output. And so right on the natural frequency, you have an unbounded output. So although we focus on the definitions of stability in terms of their free response, so the ones that I highlighted up here, these ones, it's good to understand BIBO stability as well. There are certain cases where that is pretty important. So, okay, that's all I've got for you. Thanks for staying a little late today.